You know, for millennia, we've had this picture of prime numbers as these fundamental building blocks of our universe. Numbers like 2, 3, 5, 7, they're like the indivisible atoms of arithmetic, just a static, unchanging list of numbers that we go out and discover. But what if that entire picture is wrong? Now, I know that sounds a little weird, right? But stick with me, because this question leads to a profoundly new way of seeing things. What if primes aren't these static objects we find scattered along the number line? What if they aren't really numbers at all, in the way we usually think of them? Well, this is the absolutely beautiful and, frankly, radical idea from the work of mathematician Sunyon Hong. He suggests that primes aren't objects, they're events. Specifically, they are moments, well, moments on the number line, really, where a deep, fundamental wave crosses a simple straight line. The primes literally are born where the wave meets the line.
Okay, so to even see this wave, we first have to build the signal that carries all the information about the primes. Think of it like this. You can't hear the music on the radio until you actually tune into the raw signal that's floating through the air. We have to do the same thing for primes. And the tool we use for this is something called the von Mangold function. Now don't worry about the name. Just think of it as a special prime power detector. As it scans along the number line, it lights up only when it hits a prime number, or a power of a prime, like 4, which is 2 squared, or 9, which is 3 squared. It gives a specific value to those points, and for everything else, it just gives a 0. It's a way to create a signal that only cares about the primes.
All right, let's actually build this signal together step by step. We start at 0. When we get to our first prime, 2, boom, we jump up by an amount equal to the logarithm of 2. Then we stay flat until we hit 3, and we jump up again, this time by log of 3. Then at 4, that's 2 squared, so our detector pings again, and we add another log of 2. At 5, we jump by log of 5. And we just keep doing this over and over for every single prime and prime power, creating this cumulative rising staircase. And this is what you get. This jagged staircase graph is our signal. It might just look like a jagged mess of steps, but trust me, locked inside this graph is everything. Every jump, every riser contains the complete raw data of the entire prime number universe. Okay, so we have our signal, but just looking at it like this, the deep pattern is still totally hidden. To see it, we need to change our perspective. We need to look at it through a very special kind of mathematical lens. And that lens, it's the logarithmic scale. Here's why that's so crucial. It's like a kind of mathematical magic trick. It transforms the world of multiplication, which is how numbers normally work, into a world of addition. And that is the natural language of waves, of frequencies, of music. So when we apply this new scale, what happens? Well, the places where our prime events happen, they're not at 2, 3, and 5 anymore. They're now at the log of 2, the log of 3, the log of 5. They're spaced out in a totally new way. This whole transformation basically arranges them perfectly for wave analysis, almost like they're notes on a musical stuff. All right, so we've got our signal. We're looking at it through the right lens. Now comes the truly amazing part. We're going to use this incredibly powerful tool from number theory called the explicit formula. And it's going to act like a prism, splitting our signal into its two most fundamental parts. And what we get is, well, it's just incredible. On one hand, you get a simple, smooth, perfectly predictable line just rising upwards. That's kind of the average trend, the boring monotone part of the signal. But on the other hand, you get this incredibly complex, oscillating, intricate wave. This, my friends, is the famous music of the primes, and its strange frequencies come from the mysterious zeros of the Riemann zeta function. So we've broken the signal down into two pieces, a simple line and a complex wave. Now, to see where the primes are actually born, we've got to put them back together. So this leads to the big question, right? What happens when we put these two things back on the same graph? What happens when we overlay that complex dancing wave right on top of that perfectly smooth reference line? To figure that out, we just need one simple rule. We'll call it a crossing event. A crossing event happens at the exact point where the wave physically crosses the reference line. It's the spot where the distance between them is exactly 0. And here it is, the incredible payoff. The places where these crossings happen, they are not random. The very first time the wave crosses the line happens at t equals the log of 2. The next crossing, the log of 3. The one after that, the log of 5. It's perfect.
The crossing points line up exactly with the logarithmic locations of every single prime number.
So this is way more than just a cool math trick. This discovery literally forces us to rethink what a prime number even is. And let me be super clear about this. This whole wave and line thing isn't just a nice metaphor. It's a mathematically solid reality built right from the foundations of number theory. And what it means is that primes are no longer these static things we just find lying around. No, they are generated. They are dynamic events created by the interaction between these two fundamental structures. The author of the paper, Soon-Hin Hong, just says it perfectly. He writes, prime numbers are not introduced as indivisible atoms, but appear as discrete events generated by phase misalignment. That phase misalignment, that's just a fancy way of saying the difference between the wave and the line. Primes are born right in those moments where they just can't stay in sync. You know, this whole journey really shows how a simple change in perspective can unlock a hidden, dynamic reality behind something we all thought was fixed and static. And it leaves you with this really fascinating question. What other profound patterns, not just in math, but in physics and biology, in the universe, are just sitting there, waiting for us to find the right way to look at them?